So welcome, my name is Haley, and I work with the Columbia Mountains Institute of Applied Ecology, and that's CMI for short. And you've joined us here today for the 6th season of CREDtalks. Those are the Columbia Region Ecological Discussions. The CREDtalks this season is going to explore the theme of climate disruption in the Upper Columbia Basin. We'll be welcoming 8 scientists to address projected impacts, potential for adaptation, and what we can do with ecosystems that might in fact help towards mitigation. If you're in attendance today, you've likely seen the impressive list of speakers to come. And if you're reviewing this recording, I encourage you to visit the webpage to learn more about the full suite of speakers in this series. And you can find that information at www.cmiae.org. You should see that address on the top right-hand side of your screen there. Today, we're going to hear from Dr. Brian Menounos, who I will introduce in more detail in just a moment. But before I do that, I would like to say thank you to the Columbia Basin Trust, who have financially supported this series, and gratitude to them for providing the funds that we needed to get this series off the ground. I would also like to thank all of you. Without your generous support and donations, this project would not be possible. So thank you very much. And we also thank anyone reviewing the recordings at a later date who may be able to provide a little bit of a donation, and that supports the production costs associated with the CREDtalks series. Now, before going any further, I would like to acknowledge and honor the 4 nations on whose territory I broadcast from today in Revelstoke, BC. And that is the Sinixt, the Ktunaxa, the Secwepemc, and the Silks. And I actually invite you to provide an acknowledgement as well. So if you would open your chat box, you take your mouse to the lower part of your screen and you'll see a control panel pop up there. And if you click open your chat, I invite you to introduce yourself if you like and provide your own acknowledgement. Where are you zooming in from today? And it takes a little bit to type those out, I know. And I see that a few people have already done that who were here last week. Thanks for hopping right on board. As those start to flow in, I'm just going to take an opportunity to tell you a little bit about CMI, your host organization for this series. So CMI is a nonprofit society and an association for people working in the various fields of ecology. Our home range is southern British Columbia, Canada, but increasingly we see membership from across BC and into Alberta, the Yukon, and the Northwest Territories. One of the main things we do is provide professional development opportunities, and those tend to come in the form of conferences, courses, and webinars. Last week, I gave a list of examples of those sorts of courses and conferences and webinars, but I'll skip that because I know a lot of you have already heard this intro. But if you weren't here last week and you want to learn more about us, of course, go to the website, so cmiae.org. If you click on past events, almost all of our past events from the last, 12 years or so are there. And there are proceeding documents on there, which are really fantastic resources from our larger events that we've held. Our typical audience is well captured by the mix of people who have registered for this event today. So I've seen representatives from environmental consultants, academics, students, industry representatives, nonprofits, First Nations governments, and provincial and municipal resource managers. So what I'm going to do now that we've talked a little bit about who CMI is just get into some of the nitty-gritty details, a quick Zoom orientation for you. For the best experience today, I would recommend that you take in the webinar via speaker view. So if you don't know how to adjust your view, you can hover your mouse to the top right-hand side of your screen and you should see a little button that says view. You can click on that and some options come up, and I would recommend that you choose speaker view. This webinar is being recorded. The recordings themselves will be posted to our event webpage within about 1 week of each live event. So I encourage you to visit that for past recordings and the other recordings as they become available. In this webinar format, attendees cannot turn on their cameras and everyone's been muted. So if you're trying to turn on your camera, you can rest assured that it won't be possible. If you would like to be unmuted, however, to ask a question, for example, at the end, you can use the raise hand function. And again, you'll find that little hand, there's a little hand on the bottom control panel of your screen. You can click on that raised hand, and that'll show a little raised hand in the attendee list for us, and we'll be able to unmute you if you so wish. You could also send us a chat to hosts and panelists if you wanted to get us to unmute you, or if you're having some technical issues, you can send us a request that way via the chat, and I would just send that to hosts and panelists, and that'll get your facilitation team. I'm going to lower my hand now by clicking on the lower hand. The chat is there for you to share resources with one another as well, but we're not going to put questions in the chat. So what we're going to do for questions is we're going to direct our questions to the Q&A box. So we're using the Q&A feature for questions. If you click on the Q&A at the bottom of your screen, again, you'll have a box that pops up, and in there you'll have the opportunity to ask questions. Now, if I could get somebody, perhaps Pete, to put in a sample question, a couple questions in there so that we can see what that looks like. I'll just show you some options once that question is up. You are welcome to add questions over the next hour as they come to you, but we're going to be holding questions until the end. And what we're going to do with those questions, if somebody asks a question, I don't see that anybody's typed one in yet, but if somebody from the audience there could type in just any random question into that Q&A, that'd be helpful. Perfect, thanks, Catherine. So she says, when will it stop snowing? Very good question for Revelstoke, BC. And you can see there's a thumbs up there, and some people have upvoted that question. So if somebody asks the question that you want to see answered, click on that thumbs up, because I'm going to relay the questions in the order of popularity at the end of the talk. All right. I think that's it. Now that that's done, let's move on to the real reason why you're all here today. I would like to welcome Dr. Brian Menounos, who will present recent and projected changes in snow and ice in the Columbia Mountains Basin. So Brian Menounos is the Canada Research Chair in Glacial Change, and he is a professor of geography at the University of Northern British Columbia. His research group studies the response of alpine glaciers and mountain snowpack to climate change, primarily through the use of satellite, airborne, remote sensing technologies. Brian and his team have worked on understanding changes in snow and ice in the Columbia Basin since 2005. So I'm going to pass it over to Brian. Thanks very much. Brian, you can go ahead and share your screen over mine.
Thanks, Haley.
Thanks.
Okay, I'm hoping everyone can see my slide and hear me. I'm going to assume if I don't hear from Haley.
You look
great.
and great.
Okay, thank you very much. I would like to take the opportunity to thank both Haley and the Columbia Mountains Institute, and also the Columbia Basin Trust for providing some of the funds for this. And today I'm speaking to you from Prince George, which is within the unceded territory of the Lheidli First Nation here in Prince George and the surrounding area, where I work, play, and enjoy my time in beautiful British Columbia. I'm going to talk to you today about changes in the cryosphere, so forms of frozen water, and in particular, I'm going to talk and primarily focus on alpine glaciers in the Columbia Basin. I was hoping that we would have enough time to talk about changes in snow, but primarily just due to time constraints, I've decided that we have enough to really discuss with respect to how glaciers are changing in the basin itself. So one of the things I'd like to point out is that how is the first and the second speaker of these CREDtalks related? Well, I had a chance last night to have a look at Mel's presentation on YouTube. Unfortunately, I was committed, so I couldn't see it in person. And Mel Reisner and we first met in Colorado many years ago, where Mel taught me how to actually write a scientific paper. So one of my first papers from a graduate degree was with Mel, and it was actually doing some winter coring at this lake. This is Sky Pond in Lockvale in the Colorado Front Range, where I remember skiing down with lots of mud and Mel by my side. I was also told that Mel was worried about being labeled as Dr. Doom. So I put this little slide in here for Mel to remind us all that even though sometimes the science we do might be a little bit depressing, the actual interaction with people and policymakers and those that are using the information that we gather, that's part of the enjoyment, but it's also fun to explore the science, even though there may be a depressing end result with respect to glaciers, for example. So I want to talk to you a little bit about the talk today. So I'll just introduce what I mean by the cryosphere and why it matters for Earth and Earth's future. I also want to talk a little bit about ways to observe it. And I'll give you some examples by recent glacier change in the Columbia Basin. And then finally, we'll get on to thinking about expected changes in glaciers throughout the remainder of this century. And what I hope that you take away from part of the talk is that some of the changes that we'll see are highly nonlinear. So this draws upon one of the concepts that Mel brought up last week, this idea that things are happening now at accelerated rates. So we're seeing changes not just in, for example, greenhouse gas emissions and concentrations in the atmosphere or temperature, but we're also seeing the direct response of snow and ice. So when we talk about the cryosphere, we're really talking about all forms of frozen water on Earth's surface. And so this little cartoon from a report about a decade ago shows the different components of the cryosphere. So whether we're talking about sea ice in the Arctic, we could be talking about the great ice sheets, the Antarctic and Greenland ice sheets. Or if we go a little bit closer to home, we can talk about things such as lake and river ice, snow that seasonally drapes or blankets the mountains, and then small ice bodies or ice fields that we have in Western Canada. All of these are important in terms of the water that they provide, but they also provide that important reflective property. So in the case of high latitudes, the seasonal snow and also the Arctic sea ice provides one of those ways that we can reflect incoming energy from sun back to space. And without that, we start to see an acceleration of surface temperature, both regional and in some cases hemispheric, as we've seen in the last few years. So getting a little bit closer to home, I'm going to focus primarily on the Columbia Basin. It's one of our largest drainage basins in North America. And by and large, most of the surface flows from the Columbia Basin, whether we're talking about the Canadian portion or the entire watershed itself, is largely driven by seasonal snow and the timing of when that seasonal snow melts. When we talk about glaciers, though, by and large, the vast majority, practically all of those glaciers are situated in the Canadian portion of the Columbia Basin. There's over 2,000, and collectively they cover anywhere from about 17 to 1,800 square kilometers of the land surface. Now, even though it's not a dramatically large source of water, it's the timing when this water is released to many of these headwater streams. So in late summer, when seasonal snow has been melted away, this is where the melt from the glaciers themselves starts to kick in. And so some of the red stars that you see on these are study sites where, by and large, my former PhD student, Ben Pelto, as part of his PhD, was looking at the seasonal mass balance. And we'll talk about what that means in a moment. So he by and large, did most of his PhD on these glaciers in the Columbia Basin. So I also acknowledge and thank him for some of the information that I'll be sharing today. So when we look at glaciers and think about glacier change, we are fortunate in Western Canada to be able to dial it back in time. So this is one of the original photos from 1901 from H.O. Wheeler, who was doing some of the topographic surveys throughout the Columbia Basin in Western Canada, showing Mount Sir Donald and the adjacent Illecillewaet Glacier. And in 2011, the Mountain Legacy Project went back, Eric Higgs and company, to sort of do comparison photos. And I'll just flip back through those because it's rather dramatic. So we see that these glaciers have undergone profound change over the last 100 years. And we'll see that, unfortunately, many of these glaciers do not have a long life for the remainder of this century as well. So a little cartoon here just to show you and to think about what we mean by glacier runoff versus glacier wastage. Imagine a glacier that is in equilibrium with climate. That is, the amount of input equals the amount of output. So it's not thickening, it's not thinning, it's not losing water due to what we refer to as glacier wastage. When we think about the Columbia Basin or times before it was regulated, we might see that by and large, the hydrology or the surface runoff is really controlled by the timing of seasonal snowmelt. So anytime between April and August. Once you start to regulate a watershed, you can start to change some conditions, largely due to flood control in the case of the Columbia Basin. So you're often reducing the peak flows. And in some cases, you're also increasing or elevating the base flows during non-nival or non-snowmelt conditions. The glacier runoff is this component that I've illustrated here in this cartoon. This is this green component of the hydrograph. So again, if the glacier was in equilibrium, it wasn't retreating, wasn't growing, we would see that by and large in late August, end of July, depending on the season, maybe even into September, we would see runoff coming off the surface of these glaciers and at the toes, simply because the ice is low enough in elevation and undergoes melt. But the mechanics or the dynamics of the glaciers allow that lowest part of that ice to be replenished through what we call mass or ice dynamics. So there is this redistribution of ice from high elevations to low elevations. The situation, though, in a time of a warming climate is such that you're not replenishing that ice to lowest elevations fast enough. And as a result of that, the glacier retreats. So we refer to what's considered to be glacier wastage. So this is the component of flow which is not replenished. That is, this is you can think of this as sort of money that's being withdrawn from a bank and not being replenished from your weekly paycheck. So you can't do this forever, and glaciers need to have continued replenishment or cool conditions to sustain themselves in a given climate. And so future flows for the Columbia Basin or any mountain basin in Western Canada might be expected to see a shift to earlier flows in the nival period, so the times of spring runoff. There may be also a reduction in the peak flows, although it depends on what year we're talking about. And this component, which is actually then not replenished, will be forever gone in terms of this glacier wastage. So in times of glacier retreat, we often will see a bit of a kick up or a bit of an excess water, but that is not sustainable long term. So Mel talked about this. This is a graph that's produced by NASA from the Goddard Institute of Space Studies showing the temperature anomaly. So deviations between the average temperature 1950 to 1980 as a what we call a climatology or a climate period. So these are deviations from that. And this is the record that we have to assess or detect the current change in the climate system with respect, in this case, to surface air temperature. This is the most recent global climate models or general circulation models, both are used for the most recent IPCC assessment. So I've taken all of these models, I've averaged them together. And what you get here is this green line, which represents the long-term ability of those GCMs to produce or to represent the surface air temperature for Earth. What these GCMs were never made to do is to sort of predict any one particular year. But more importantly, these GCMs were meant to capture the decadal variability and also the trend that's experienced. And by and large, they do a fairly good job, even with the most recent assessments. When you actually look at what's in store in kind of a worst case scenario, so Mel introduced this concept of SSP 8.5, that number just represents the amount of additional energy that would be coming into Earth's atmosphere in watts per square meter due to greenhouse gas or global emissions and changes in land use. So things that humans themselves are doing. So you can take this as a worst case scenario. The unfortunate thing is we seem to be by and large on track for that worst case scenario. What does it look like in terms of surface temperature? So if we were to look at a 1 degree world, we might actually see, for example, that there's not as much dramatic change with respect to the differences in latitudes with respect to surface warming. When we actually look at the worst case scenario, so this is the high emission scenario, we start to see not only that there's a greater magnitude of warming, but much of that warming is located or concentrated at highest elevations. And that does not bode well because we have the great Antarctic ice sheet in the southern hemisphere, and also the Greenland ice sheet, and also Arctic sea ice. So collectively, this worst case scenario does not bode well for the cryosphere and changes in how reflective these surfaces are in mitigating the amount of energy coming in from the sun itself. It's also expected to get wetter. So one of the outstanding questions that we had a number of years ago when we started looking at glacier change in the Columbia Basin was, would this excess precipitation counter effect the warming that was expected? And by and large, as we'll see at the end of the talk today, that's not the case. Simply not, or it's certainly not due to the earlier studies that we did, and also some of the more recent studies that I'll conclude. When we also look at regional climate change, so this is from a IPCC report that was put out on the state of the oceans cryosphere several years ago. It's showing the Rocky Mountains, but this particular study or this review considered most of the mountains in the Canadian Rockies, which also included the mountains in the Columbia Basin. So by and large, it's similar. What we're seeing is that there are expected changes that differ depending on the emission scenario. Again, the light pink is the low emission, the darker red is the high emission. We're seeing, and with respect to snow water equivalents, percent changes that are getting close to 60 to 80% for a given year on average. We're also seeing, not surprising, this increase in surface air temperature, both in summer and winter time. And this is happening at low elevations, but also at the mountain tops where many of these glaciers exist. Okay, so I want to transition us a little bit and talk about how and why do we measure glacier change. And the first point is, why are we out there measuring in the first place? These observations, in a similar way as meteorologists will collect observations of the current weather, in many cases is to improve our theoretical understanding of both the atmosphere and atmospheric dynamics in the case of a meteorologist. In the case of glaciologists, we actually are collecting these observations to refine theory and to improve models going forward. So that's by and large what my research group is interested in: collecting observations working with other groups to improve the modeling and theoretical advances going forward. And we can do this in a variety of different spatial scales and also over different temporal scales. This little cartoon is from an investigator in Colorado, which we've modified to just show some examples of ways that we can measure both glaciers or seasonal snow, if you will. We can use anything from individual point measurements on the glacier surface. We can start to use drones or photogrammetry, so the old way of actually doing digital elevation models. And we can go all the way up to spaceborne observations, or if we're lucky enough, have access to an aircraft and do repeated measurements. So this is from a study in 2019. It's already outdated, as you can imagine. Landsat 9, which is a new satellite, which is publicly available data. It will be available, I believe, in a month or two. This was successfully launched. But this just gives you an idea of the rich treasure trove of satellite information that we have to say something not just about glaciers, but the land surface and how the land surface is changing. So this comes in different flavors, whether it is publicly available and shared to the public, or whether it is commercial images, which are available at a cost. But we are lucky enough to have the access, as we'll see, to much of the publicly readily available imagery for the analysis that we do. And much of what I'll talk about today is we're dealing mostly in the portion of the electromagnetic spectrum where we can actually sense. We can actually see through our own eyes much of what's happening. But in some cases, how reflective the surfaces of glaciers or the snow surfaces, it starts to drop off as we get into the shortwave infrared portions of the EM spectrum. So this is an area where we actually can't see with our eyes. And in many cases, snow and ice surfaces appear dark. So we can use this difference between their brightness in the visible portion and their darkness in the shortwave infrared portion to reliably construct the extent of existing ice or existing snow patches, and then have a better way of mapping those surfaces and protect against things like water, and in some cases, shadows. What we'll also use in some cases is LiDAR, so this acronym, light detection and ranging. So this is really a technology that shoots out many hundreds of thousands of individual pulses of light, in some cases per second. We get those returns back, and if we know where the aircraft is, we figure out what's called the time of flight, and we can figure out the elevation, or through repeated surveys, the elevation change over these surfaces. Okay, so I introduced this concept of mass balance or a budget. So when we consider glaciers, and the example that I used was Ben's work in the Columbia Basin. So he went out quite reliably twice a year and measured for 6 different glaciers, 4 sometimes, 6 for others, how much these glaciers accumulated water in the wintertime, how much they melted in the summer. And by adding those 2 terms together, we can get what's called the mass balance. And so we can go out to the field, we can dig snow pits, we can probe, we can estimate the density of that snow, and we convert that to a water equivalent unit. It's a little bit easier in the summertime because you simply are putting in what are called ablation stakes, and you measure how fast or how much those have lowered through time. And so then we can convert that to water equivalent by knowing the density of the ice. And we add those 2 terms together and we get what's called the mass balance for these glaciers. It's time intensive. It is the standard way of measuring the health of a glacier. But when you consider that the Columbia Basin, for example, has over 1,800 individual glaciers, you start to realize this difficulty in choosing those glaciers that you're going to measure, and more importantly, asking whether they are representative or not. So one way we can circumvent that is we can also use spaceborne techniques, but in this case, this is an aircraft which we cooperate with the Hakai Institute. This is a wonderful organization that I've had the privilege of working with to understand not only changes in snow and ice, but just changes of the land surface. And so we use what's called the Airborne Coastal Observatory as a way to document in detail changes in the land surface for areas that we're doing scientific study. So in our case, it's the snow and ice. And even though it's called the Airborne Coastal Observatory, we consider the Columbia Basin to be ultimately the headwaters of the ocean itself. So that's one of the reasons that we are collaborating on the work in the Columbia Basin. Some of the areas that we have surveyed repeatedly over a number of years. I won't go into any great details, but these are just, these pink polygons are showing the regions that we routinely survey twice a year. So in the case of the Columbia, they are the glaciers that Ben was studying, all the way from Castle Creek Glacier, which lies just over the edge of the, and drains into the Fraser Basin, but we also routinely survey the Peyto Glacier and the Yoho ice field, and also the Columbia ice field itself. So this little cartoon here is just showing you what the surface elevation model, now illuminated with artificial light, so we're producing what's called a hillshade image. This is just showing the snout of the Kokanee Glacier, so one of the glaciers Ben has studied from about 2015 to present. So just showing, not surprising, I guess, is that the glacier is undergoing retreat. So again, this lower part of the glacier is that component which we refer to as the glacier wastage. So this will contribute water to the glacier itself. But recall again that we have to do this for many hundreds of glaciers to get a good representative sample. And that again is why we use an aircraft to do this for hundreds of glaciers in the Columbia Basin. Well, how well does it work? When we compare our results to Ben's work, so that's this OBS, this is observed mass balance, both for the winter, the red is showing the summer, and then the gray or black bars represent the average. So we take those two terms and we add them together and we get what's called the net mass balance. So regardless whether you do it with laser altimetry, that's what this ALS is, or the observations, they agree within errors or within the uncertainties. So it gives us some credence or some faith that what we're seeing and what we're measuring from an aircraft is reliable and a good way to do this going forward. When we look at the cumulative mass balance, so that is, let's take the measured mass balance and add those terms together. If the glacier was in climatic equilibrium, we would see this cumulative mass balance curve more or less fluctuating around the zero line. And there's going to be years of gain, years of loss, but by and large, we might expect to see more or less a random walk along this zero line. That's not the case, and certainly not been the case for most of our glaciers in the last 50 years. Here too, you can see the comparison of the cumulative loss versus the observed loss. And not surprising, I guess, to most of us is that 2021 was an especially bad year for the glaciers in the basin. Here's looking at it another way. So this is the elevation change. I believe it's elevation. I'm covering up just need to minimize my thing here. This is height change, same thing as elevation change, that shows the surface of the glacier and how much it underwent thinning over the last year, or that is from the end of summer 2020 to the end of summer 2021. So clearly there's been no area, or maybe a little pinprick of region that actually experienced thickening. So this is not a good news story for Kokanee Glacier. In fact, Ben calculated out that it lost something like about 6% of its total volume in 2021 alone. So it was a really, really bad year for the glacier. Why was it so bad? This really illustrates the point. It was largely above average, and in some cases, the record warmth during the particular year. This graph on the right, or this map, is from the Pacific Climate Impacts Consortium. This was put together by my colleague Farron Anslow, showing the different regions that we study glaciers and recognizing, at least on the meteorological data, that the lower portion of the province really experienced record warmth. So it was not just during the heat dome in late June, but it was also following warm conditions during that last summer. And the reason the heat dome was so bad, we think, for the glaciers is that it so rapidly melted this protective insulating snow cover and allowed the ice on the surfaces of these glaciers to be exposed for a much longer period of time, wholly unlike they've seen in the past. This graph or this map on the left shows the anomaly in Kelvin. Just these are anomalies, so you could just treat this K as a degree C. But you can see that by and large, the week of the heat dome, we really experienced exceptional records relative to the 1950 to present day anomalies. So that means that for each of that week-long period from 1950 to present, last year was something like 10 to 12 degrees warmer. So that is a lot of energy that you're introducing to the glacier surface. Why was it also bad? Well, if we looked at the black carbon modeled by NASA, this is what's called a reanalysis, and this is showing the summers between 1950 to 2021 and what's called the black carbon flux. So black carbon is the soot that's introduced by wildfires, and that will also change how reflective these surfaces are. And what you can see through this little animation is that 2021 in particular, not only was it warm, but it was also the wildfires themselves were introducing a lot of dirt, if you will, black carbon soot to these surfaces, which then can absorb more energy coming in from sunlight. So it's almost a 1-2 punch that was really bad for glaciers. Okay, so what about all of the glaciers? We used to do what was called epoch analysis. So we would sort of consider these glaciers and try to understand the area change of the glaciers from one period to the next period. So this was largely simply due to the availability of satellite imagery. In some cases, we had gaps due to there was just no available data. Sometimes one had to ask the question, which epoch do you use, which period of time do you use, and how do you compare it? So collectively, worldwide, it created quite a spotty situation. So I refer to this as truly old school. This is the way that we used to do this sort of work. What we've really seen in the last couple of years is sort of an idea of treating the data as stacks of data. So I'm sorry, it's lunchtime for me. I'm getting a little hungry. So if you like pancakes, I apologize for the pancake slide. But you can treat these individual pancakes as any given year or any given month of data. And we're just interested in looking at the trends through the stack of pancakes. So in the case of elevation, we might be able to stack all of the elevation maps and then look at how that elevation changes through time. We can do the same thing with glaciers and polygons as well, as we'll see in a second. So this was a study that I was fortunate to be part of. Roman, the lead author, worked with my group a couple of years ago, and he was interested in trying to quantify how glaciers were undergoing mass change, not just in the Columbia Basin, but throughout the world. And so one of the things he used is he actually used what are called aster images. So this is a spaceborne sensor that acquires or collects stereo imagery all over Earth's surface. And it does so and has been doing this since about the year 2000. Some of the more recent shortwave infrared imagery coming off of the Aster platform is no longer usable due to a sensor failure, but we can still access and analyze the stereo imagery. So in much the same way that we can look at air photos and how they used to make topographic maps, we can actually use this imagery from space. And then once we create these elevation maps that have been corrected for biases in orbit or the trajectory of the satellite, we can actually start to then analyze the elevation change. And so we were also lucky enough to use and have access to lots of compute power here at the university, where we created and produced these elevation maps for all of Earth's glaciers. And what you see when you do this is that Ramon was lucky enough to get about 97% of all areas on Earth's glaciers covered. And it represents on average about 40 individual pixels or 39 observations through that pancake stack. So imagine those pancakes, each of those being 1 year of Aster digital elevation data. So we have now 39 or 40 on average to look at any particular location on the glacier. What does it mean closer to home? Here's an example, just as a way to distill the results. This is the first decade of the 21st century. All of the glaciers in the Columbia Basin are shown as colors here. And you can see that, at least with this color coding, there's a fair amount of white. So the elevation is close to either zero or perhaps even a slight gain. So on average, collectively, those glaciers lost about 0.4 gigatons of water per year. So a gigaton is a cubic kilometer of water. The last decade, that rate doubled. It more than doubled. So again, just flipping back and forth, you can see that at least for the last decade, the rate doubled. And if I were to do this for the last 5 years, you would see the rate increasing even more. And again, this reiterates the point that Mel was making in that we're starting to see an acceleration of many of these changes, not just in the atmosphere and the greenhouse gas emissions, but also the direct response, in this case, the cryosphere. But what about area change? This was a paper that one of my students, PhD students, just released a couple of weeks ago. And this actually looks at using the Landsat record to look at area change for all of the glaciers. And I'm going to focus mostly on the Columbia Basin again. So I'm not going to go into the details here for time, but this just gives us an idea of all the steps that are required to take the publicly available data in the top left here and get all the way down to the lower right to start to come up with individual polygons of all of that rich data. He dealt with, I think it was 5,000 or 10,000 individual Landsat scenes, and he did this in Google Earth Engine. So what's the take-home message? Here's the trend for the Columbia Basin, all of the glaciers showing the year-by-year variation in his estimate of the area of the glaciers. Not surprising, you see some changes here, but you can see that the trend is by and large nonlinear. And so this is why we refer to the accelerated loss, not just in the mass, but also in the area. The red dot here represents data he just crunched this morning at my behest. And so it shows that it is indeed a record loss that was experienced last year. And again, largely due to unusually warm conditions, but probably also due to wildfire. Okay, so what's going to happen in the future? I've got a few more slides here, and then I'll turn it over to questions. A number of years ago, and this was at the beginning of my talk, I mentioned that we were interested in, when we started working with the Columbia Basin Trust and others in the Columbia Basin, we wanted to understand whether the projected increase in precipitation may counter effect the warming that was being experienced. And in order to do that, you have to understand something about the climate. And that's where we take the climate fields from these general circulation models, and we have to perform what's called downscaling. So we take that low resolution climate data and we move it down to the individual glacier surface. And we also have to then nourish or melt the glacier, and we use what's called a glacier mass balance model. And then finally, we have to then take that mass that's accumulated or lost each year and move it from the top of the glacier down to the bottom. So that's what we talk about with respect to the ice dynamics. So this little flow diagram just shows what we have here. And at least in 2015, when Gary Clark, who's now an emeritus professor, he published the sort of the capstone paper from Glacier Network, which we had a number of years ago, looking at the different scenarios here, this RCP 2.6, 8.5, these are, the number is the same as the more recent assessments that Mel introduced and that I talked about earlier, these socioeconomic pathways. The number again represents the radiative forcing that would be different at the end of the century due to land use and human introductions of greenhouse gases. And what we see here is that by and large for the Columbia Basin, at least for this 2015 study, it's not a good news story. That is, by 2100, most of the volume of the ice is lost. There is some difference between the low emission and high emission scenarios. And if you were then take these curves and change them into rates of change, Gary had predicted that by about 2030, we will see a peak in the glacier wastage component. And that's really been sort of reiterated in subsequent studies. And I'll just leave you with 2 more slides here. This is a ongoing work that I believe is now in review, looking at trying to update some of the work that Gary did, but in this case, David and co-authors are doing this for the globe. So for all the individual glaciers on our surface, using the ice dynamics model and trying to come up with the best estimates using the new IPCC assessments. And by and large, it's the same story, unfortunately. So using the newest emission scenarios, anywhere from about the 2.6 to the 8.5 in terms of area. Unfortunately, the Columbia Basin is expected to lose most of its ice, both in terms of area, but also in volume. There's a little bit of difference towards the end. The other point I'll make is both the earlier study and this one show that there's not a lot of dramatic difference between the different emission scenarios until about mid-century. But unfortunately, at that point, we've already committed, because these glaciers have memory, and what we do today will not really be felt by the glacier for several decades going forward. So I would agree with Mel, we really need to be getting our act together. I'm also a bit pessimistic whether we collectively will be able to do that. So I'll leave you with some conclusions. I hope I could show that advances in how glaciers respond to climate will improve through continued space and airborne observations. We used to be hobbled to some degree by the computational efficiency and the availability of data, but by and large, that's no longer the case. And unfortunately for the ice in the Columbia Basin, it shows accelerated mass, but also area loss. And the newest projections using better physics, but also new emission scenarios, largely accord with earlier work. We are seeing, and people have shown that the newest modeling is showing some differences in other areas where large scale dynamics are important, tidewater glaciers, for example. So even though they're not showing a dramatic difference for the Columbia Basin, they are showing some interesting results worldwide. And so with that, I will acknowledge the Columbia Basin Trust largely for supporting much of the earlier work and also for the talk series, Global Water Futures, NSERC, who provides support for my research group as a faculty member. BC Hydro has also been exceptional in their long-term support of the monitoring of the glaciers within the basin. And then finally, my hat goes off to Hakai and just the wonderful scientists that work at Hakai, that it's been just a delight to work on some of these outstanding issues that are facing us and British Columbians. So I'll leave it at there. Thank you.
Thank you, Brian, very much. Thanks for your dedication to this work over the years. You're right, you weren't any less do me necessarily, but we did appreciate that early slide. We're going to open up to questions now. Looking at the time, we've got about, let me see, we've got about 10 minutes for questions. I can see that there are 2 that have been put into the Q&A so far. So just a quick recap, we're going to use the Q&A function for our questions. So if you have any questions, type them in there. If you see a question that you'd like to see the answer to, please give it a thumbs up and I'll address them in order of popularity. And if there are some questions that we don't get to by the end of the 10 minutes, it's possible that I can share those questions with Brian after the fact and we can try to get them answered afterwards. Okay, so Brian, the first question comes from Richard Johnson. And he says, how important is sublimation loss in your mass balancing modeling?
So sublimation, at least in this part of the world, is not that large. I mean, it depends on whether we're talking about snowdrift. So if you're talking about sublimation losses for drifting snow, that's the sort of physical model that is really not, we haven't run for the individual glaciers, partly because it's not trivial to downscale the wind from a GCM. That is, how do you take a GCM run and then downscale wind down to the individual glaciers? So sublimation is not one of those components that's typically done at the global scale. Great question, though.
Okay, great, thanks. Your next question comes from Becky, and she says, could you elaborate on why black carbon from wildfires is especially detrimental to glaciers?
Yeah, great question. So if you think about the energy, think about these surfaces that are bright. Okay, so we'll talk about the spectrum in terms of the visible portion. If we looked at the amount of energy coming in from sunlight, most of the energy is coming in at the yellow portion of the EM spectrum due to a thing called Wien's law. So if you actually see, most of that energy is coming in the visible portion. Anytime you can actually darken that surface, you can absorb more incoming radiation or incoming energy from the sun. So when we think about doing the surface energy balance or budget of a glacier, we have thermal energy, but we also have radiation. And so and it's a fancy word essentially for the shortwave incoming energy coming in from the sun. So if we start to change how reflective that surface is, we're going to absorb more energy. So black carbon is particularly known as a strong absorber of energy. And so that will heat up, it'll start to melt. And so anytime you can darken those surfaces, you're going to increase that melt.
Okay, makes sense, thanks. Okay, and our next question here comes from Colin, and he says, or Colin, European colleagues suggest that the rock glaciers could act as climate warming refugia for cold adapted species. What's your opinion on this? Do you measure mass or area loss on rock glaciers? And to what extent do the rock glaciers exist, I guess, in the Columbia Basin? And how do you measure or detect them?
That's a great question. I can't think of any rock glacier off the top of my head, but I know that there's a fair amount of, we call it ice cored moraine, or in some cases, it sort of almost looks like this complex junk. Okay, so this transition between the end of a glacier and this rubbly pile that looks like it's almost kind of moving. In some cases, those surfaces we think have interstitial ice within them. And what we can do in terms of the technology is we can fly over those surfaces with a LiDAR system, or if we're fortunate and can afford commercially available stereo imagery from something like worldview, we can actually see through time, we can see how these surfaces are deflating. So in some cases, we don't know yet how much of this interstitial ice exists in the Columbia Basin, probably similar to the Rocky Mountains, maybe similar to the Coast Mountains, we don't know. In terms of a refugia, in terms of aquatic ecosystems, I'd be well outside my comfort zone. But fortunately, the third CREDtalk speaker, Janice Brainey, who's going to talk next week, used to be a former student. And so there's the third link of your first three CREDtalks. And I'm sure if she was asked that question, she'd be able to tell you.
Okay, good to know. I didn't know that Janice was a student of yours. Great. Okay, thanks for that question. So now we go to Michael, and the question is, how far did the ELA, the equilibrium line altitude, move in average for the summer 2021 in the Columbia Basin?
Oh, great question. In some cases, you remember that introductory slide that I showed you, at least with the outline of my talk, that was below, I think I want to say, is it below Joker Peak? I think it was north of Kokanee Glacier. There was no, that little glacierette had no retained snow. And in fact, the Kokanee had very little. So we're talking about, when we talk about the ELA, it's a theoretical line at which the net mass balance is zero. But in some cases, we interchange that term with the transient snow line. And so answering that question, we know that many of the glaciers did not have retained snow, or very little that we could see. We're still kind of figuring that one out. That's one of Alex's additional PhD projects. So we could probably answer it in a few more months.
Okay, great. Okay, question from Ellen. What's the impact of glacial wastage on aquifer recharge? And then she has / lakes, springs, and wells, i.e. is the future of freshwater, the future of freshwater resources?
Yeah, that's an interesting question. It's one that's not explored by my group, but certainly being explored by one of my collaborators on Global Water Futures, Masaki Hayashi. Masaki is a professor in Calgary, and he, I believe, has looked at this effect in the Rockies itself. I don't know if there's been many studies in the Columbia Basin per se, but we know to some degree, whether it's melting ice or in some cases interstitial ice, that can provide some recharge. But it also looks in some cases that the flow paths are far more complicated than your cartoon or conceptual models used to think they were. So somewhat depends on this bedrock structure. But I'll take the politician's view and not answer specifically, and have you contact Masaki, who could probably give you a much more fulsome answer.
Okay, sounds great. You might take that sort of avenue for this next question as well, because I think that possibly future speakers might address this. But if and when, this is a question from Charlie, if and when glaciers cease to exist, what does that mean for water balance, water regime, local temperature, other?
Well, I think in some cases we lose the thermal buffering capacity. And so it's not just the quantity of water that's released to these headwater streams, but it's also the thermal regulation that they provide. It will have some impact. Species and ecosystems adapt. I mean, they've been adapting for billions of years. And I don't say that to trivialize the problem. In a way, it's almost, if you are looking at a time for space substitution, that is, take Montana and take the environments of Montana and move them northward. That may be what's going to happen, and that's probably a likely projected change, I would suspect. It will have implications, though. If, for example, you had really sensitive species, they will not be able to tolerate a thermal stress in that environment. But we also, the other non-aquatic, I know it's an aquatic series, or sorry, the ecology, but it's also humans. And I came to British Columbia because I loved the mountains and the glaciers. They wouldn't be beautiful without glaciers. So not having the glaciers also impacts tourism, just I would say our mental wellness in some cases, and our cultural heritage. Certainly, if you asked the original people that lived in this land thousands of years ago, how would they feel losing these icons? I think they would actually be pretty sad about that.
Yeah, so true. Thanks for saying that. Okay, our next question, it's 1:02, so I know you're short on time, but there's just 2 questions
Oh,
left.
I can be a few minutes late. It's just a department meeting. Oh,
Okay,
wait, this is recorded.
Not just. Okay, great. Next question comes from Jenny. A lot of regional planning and urban and suburban development is still based on current water quantity, which is linked to glacier meltwater. Water availability can be a limitation to growth. Is your work being shared with local government planners so that they know they should be basing their approvals on new housing developments, for example, on future, not current water availability?
That's a great question. We, as a university scientist, we tend to publish our results, but we also interact and work with both the provincial and federal governments to make our data available. And in some cases, for the people of the Columbia Basin, when we used to work more closely with the Columbia Basin Trust, we would share our data, and we're happy to do that. The point being is that in some cases, it's the individual communities that may reach out to us. The other unfortunate thing we have in British Columbia is, unlike a country like Switzerland that has many dozens of glaciologists all working in an area the size of, you could take Switzerland, and it'd be about 40th of the size of BC, 1/40th. And so you have many more glaciologists, and in particular, you have government scientists. So we try to do our part, but I really think in some cases, government needs to step up and really start understanding the importance of glaciers and seasonal snow, and reinvigorate monitoring programs.
Right. Yeah, absolutely. Thanks. Okay, so we've got one more question here from Kat, and then if there's time, I might sneak in one of my own. So Kat says, where can we access the previous work or publications that were supported by CBT? Would you be able to provide report titles? And if possible, you could probably send those to me and I could email them out, perhaps, if that's easiest.
Sure, we have submitted reports before. There's also a report that we did, I think we released in 2020. It should be available online. I think it was a snow and ice report in the Columbia Basin. That should be available as a PDF online. And certainly with respect to the projection work, I guess that paper might be under paywall, but certainly anyone who contacts me, I'm more than happy to share a copy of that. The stuff that I showed at the end is still sort of, it's undergoing review, so I wouldn't be comfortable sharing that until it goes through peer review. So.
Okay, sounds great. Yeah, you could also send me the links and I could just add them to the webpage under the talk description if that's easiest.
Sure.
Great. Okay.
If that helps.
Okay, great, thanks. You can feel free to dismiss this, but my thought was, I know we were limited for time and you couldn't address snow. I just wondered if you had any higher level sort of summary type comments you could make about snow change.
Yeah, no, thanks for that. And I apologize that I sort of spent too much time on glaciers. So the modeling, I have a former student who ran, I showed you a little bar plot that had different elevations for the expected change in snow water equivalent and summer and winter temperatures. That comes from the IPCC State of the Ocean and Cryosphere report. But I had a former student who's now finished in writing up one of her papers or one of her chapters that used dynamical downscaling. So like a GCM, except it's run at very high resolution, 1 kilometer, to look at not only could you simulate the current snow conditions, but also how might that change in a future world. And so her results largely accord with what that earlier graph shows, that one could expect something like 50 to 70% of snow water equivalent loss in the basin due to a high emission scenario. So it's not a good situation. That's not to say that there's going to be less mean annual flow. That is, the projections within the 90% credibility range shows that it's something like about 12 to 15% increase in projected precipitation. But it's the timing, and it's also the phase. So even though we might get slightly more water, if you're a sensitive system that requires cool water, then that could be a problem. So glaciers we think as thermal buffers, but certainly the seasonal snow is also providing that thermal buffer. So if it's melting earlier, or the phase change is causing more precipitation instead of snowfall, then you're getting into a situation where you're potentially thermally stressing aquatic ecosystems.
Right. Okay. All right. Well, thank you very much. I think in the interest of time, then we'll move on. There is one more question, but I know that we're over time and that you have a meeting to go to. So I'll email this question to you, and we'll get the response to the person who asked it.
I just looked at it, and I'll just say,
okay. Perfect. Okay.
I'm not sure. It's a great question. Although, I mean, we will still have ice in Greenland. We'll still have ice in Antarctica. So glaciology will continue. Certainly, maybe I could even talk to Elon Musk, and maybe we'll start doing glaciology in Mars. Certainly, I'll be dead by then.
Yeah, this our talk just got doomy. All right. Well, thank you very, very much. Thanks to Brian. Thanks again to the Columbia Basin Trust for your support. A big thank you to everybody present who donated. Again, those donations are essential, and we're grateful. A recording of this talk will be posted to the event webpage within about 1 week. That's the same for all 8 talks in the series, so feel free to send that resource out to your network. Next week, we'll be welcoming Dr. Janice Brainy, Associate Professor with the Watershed Sciences at Utah State University. She's done some really interesting research in our area, and she'll be presenting a talk on climate change impacts on water quality in the Columbia River Basin of Canada. Same time next week, same day, so Thursday, January 27, over the noon hour, beginning at 12 p.m. Pacific. More details on our webpage if you need them, and feel free to contact me if you have any questions at all. All right, thanks very much, everyone.